Well, it's nice to see so many people on this conference, and I'm really grateful to the organizers that we get the chance of exchanging knowledge because, as you probably know, it's not that common to have so many AI programmers in one place. So what I'll talk about today is our journey with implementing bots in a tactical game, in a very complex tactical game made by Acid Wizard called Soccer Kids. And the initial title of this talk was Human-Level AI Bots, and I just wanted to specify that they are purely MCTS. So it will be an interesting case study for those of you who are interested in this particular algorithm. So just a minute about me. I'm an AI programmer like for 9 years. I started my career as an AI programmer, so I was lucky enough to start with like traffic simulation and so on, and then I went on to implement AI in different, in a range of very different games, starting from those simulation games on mobile down to RTS bots, and so on. Okay, so first I'm going to talk a little bit about the game itself, just to give you the taste of the complexity and the issues that we had with the game. I'll quickly introduce Monte Carlo tree search for those of you who don't know the algorithm, and then I'll talk a little bit about building the forward model of the game and what were our challenges building that, and how we dealt with the game's complexity given the very specific mechanics that I'll discuss later, and there will be a little part regarding positioning evaluation and spatial reasoning and all sorts of issues related to spatial reasoning, and one particular solution that we used, namely polygon clipping used in MCTS evaluation functions, which is not a typical thing that you'd like to do, but it turned out to work pretty great. I wanted also to talk about debugging and visualization of this solution, but we probably won't have enough time, so I'll skip the last part just to fit into my time slot. Okay, so let's start with a little bit information about the game. So it's a turn-based game where you control a team of soccer players. It's like a backyard soccer type of setting, and the main gist of the game is that your movement happens on a continuous 2D space, but your movement fields are not constant, they are deformable. So the further you go in the initial turn, the more narrow and longer your movement field will be the next turn. So you have to anticipate what your opponent can do in response to the deformation of your movement field. So it's very complex even for human players. And there are also physical interactions, and there are different sizes of your units, so you have to take into account like real physical collisions with other players and with the ball, with the players and the walls, because you have walls on the level that the ball can bounce off of. And if you want to just see the result after the conference, you can just download the game for free. It's on Steam. It's alpha version. The project has been unfortunately discontinued, but yeah, the AI is there, so you can just see the results for yourself. And I'm really proud of that. So I encourage you to do that. All right. So of course, as you probably can anticipate, the main issue is this gridless movement system. Sorry for the cursor on the screenshots, but okay. So this is like the initial movement field, like the shape that you typically have if you're not moving. After you select a movement action, the next turn your movement field is deformed. So you have to take that into account. All right, so what were the requirements for this kind of game? First of all, the whole game mode was centered around one-on-one matches, like of two teams. So the bot had to achieve human performance to keep the player engaged. So we either had to, we thought, after some research, we decided to use MCTS because we didn't have enough data and enough time to use like reinforcement learning or other machine learning approaches. And the other factor is that we already had competent, highly performant implementation of MCTS already. So we just went with that. And Acid Wizard, the studio that developed the whole game, was kind enough to prepare a massive amount of test scenarios basically for us. So we could, after each change to the bot, we could run the game against those test cases, and this really made the whole process much easier. All right, so before I start about the problems and the solutions that we came up with, I'll just give you a quick recap about MCTS. So MCTS is a search-based algorithm that traverses the game tree in a very specific manner. It uses something called the upper confidence bound, and from this formula you can see that it scores the actions to visit. Then it selects the action that it should visit next based on the already accumulated score assigned to this action and the number of visits in this particular action. So you can see that the first term in the formula decreases as the number of visits increases, but it increases with the score. And the other one is more complex, but it does the opposite basically. It encourages exploration of actions that haven't been visited yet. And the overall flow of the algorithm is that we start with selection and expansion. So we apply this formula to select actions to get to the leaf. And as soon as we get to the leaf, we add a new child by applying an action, randomly selected. And then we traverse the tree till the end. And the end is, of course, like in typical combinatorial games like, I don't know, chess, you could even try to, if you have enough time, you could try to traverse the whole game tree to the end of the game. But of course, in a real game where you have a very constrained budget, you will have like 1 or 2 seconds to make a decision, not to bore the player. You have to terminate the simulation early and evaluate it using some heuristics, basically. Yeah, and the scores that we get from the evaluation are propagated up. So we keep score of the number of visits and of the scores for each player, and then based on that we can evaluate the action quality based on the upper confidence bound formula that I've shown you. Yeah, so this is how it would work in a two-player game. We start with the first action, we do random simulation, we accumulate the scores. In the second iteration, we do the same thing, but we select another action based on the formula. We do the random simulation till the end, and we accumulate the scores, and so on. All right, one important thing is that this simulation doesn't really have to be random. Like in the vanilla version of the algorithm, it is random, but it can be also policy guided. It can be randomized between random simulation and policy guided simulation. So there are a lot of variants of this algorithm already that have been researched. Okay, so the advantages of the algorithm is that you can adjust the quality of the AI actions based on the scores, on the quality scores that you get in the game tree. So you can easily implement difficulty levels, for example. Just instead of selecting the best action, like the highest scoring action, you can select the second best scoring action. And it easily produces difficulty levels. The very important part is that it can simulate the opponent's move, and it was crucial for a game like that, where you have to really anticipate what your opponent can do, and you want to maximize the performance. Given enough time, it should converge to optimal solutions, but of course, in practice, we never have enough time for it to converge. So it will always be an approximation of action quality, but it's a good thing because you get more variety of behavior that way. And if you're using early termination with custom evaluation, game designers can tweak the evaluation function to express their design goals. So this is something to keep in mind, that you don't always want to maximize just the quality, but you want to reflect some design intentions that the game creators had. But of course, there are many disadvantages. First of all, and the most striking one for me, is that it requires a forward model. And for some games, and for soccer kids in particular, building a forward model took a lot of time and work. It requires lots of CPU time, especially if you want to do the whole simulation, like if you want to do the random simulation till the end of the game. And it can be really hard to debug if you don't have enough diagnostic data. It's sometimes hard to understand why a given action has been selected that way, because maybe you have a bug in your forward model, but it's very hard to analyze sometimes. And the part that also took a lot of work was implementing action translation. So first you have to take the snapshot of the word state, but as you get the action label or the action that you should trigger, you have to translate it into a real world action in the game state. So it takes some additional logic to do that. All right, so to build a forward model, first you need the world state, and it was pretty easy for us because we could just reuse the data that we had in the game. So the whole representation of oh, sorry, you know what a forward model is, so I proceed to this one. So we had all the unit positions, rotations, speeds, and so on. We could just copy the world state because it was pretty well separated from the game mechanics. So we used the same system that was used for saves. So we just copied snapshot. We just took a snapshot of the game state that consisted of all this, and we didn't have to put any additional effort apart from just copying the state. But implementing actions wasn't that easy, and we had to introduce some like, apart from normal shooting and passing and moving actions that you have in the game, we had to introduce like special coordination actions, like skipping a unit, selecting a unit, and so on. But also, all those actions weren't like the real in-game actions that you would apply. So, for example, if you made a board game, you could, where you operate on an abstract state, basically you could use the whole game model as your simulator, but in case of soccer kids, where it's a physics-based game, there are a lot of async time-based components, like movement and so on. We couldn't apply those actions directly to our virtual game state, to our simulator, so we basically had to, in a way, duplicate the game logic inside the simulator. And this is the typical experience that people have using MCTS in games. All right, so the main issue with building the simulator was generating sensible actions, because right from the start we noticed that if we just sample the space densely, the branching factor would get so high that it will simply be infeasible to go through the whole search space. So what we did, we used some heuristics basically to determine which types of actions should even be considered. So this is like the basic blueprint for how we constructed movement actions. So given a target, and I'll tell a little bit more about target selection later. So let's say that this is your target, but your movement field looks like that. So what we did was the simple operation of rotating the target into the movement field and then extending into the maximum distance. And if the target was inside the movement field, we simply generated one movement position to the target and then extended it till the end. And there is no particular rationale behind that, other than that it simply does work, and it generates a sparser space sampling than just, densely sampling by angle or distance. And the target points that we used were of different natures. So of course we wanted to have a target that was that represented movement towards the enemy goal. We wanted to have the ball position. If you don't possess the ball, you of course want to move towards it. There were several specially calculated ball interception points. So like the targets of movement that would cause you to acquire the ball from the opponent. And there were a lot of special attractor points that were developed in collaboration with the game designers, basically. So they told us, as a human player, I'm looking at those particular points on the map, on the level, And they just, with their help, we implemented those special attractor points that we could generate movement actions to. So this is one example, one simple example of, so we call them unit evasion points. And basically, they allow you to move in a way that your unit ends up tangent to the opponent unit. And this allows you, I'll show you how it looks in the game in a while. It allows you to trim the movement field of your opponent, so it limits the movement of the opponent. So from the experience of human players, we knew that those kinds of points are sensible movement actions. So we just used some vector maths to calculate, to solve this vector equation to find those points that allow you to be right next to the opponent. And here's how it looks in the game. So here is our moving unit, and it moves right here. So it blocks most of the movement field of the opponent. And especially while playing the defense, it's a very useful type of action to make. And there are, of course, shooting action and passing action. So I'll just show one little example, given the time that I have, for generating shots at the goal. So we have the goalkeeper position and the clearance that you have above the goalkeeper, and we just aimed at the center. So this was like a very simple algorithm, just like a couple of lines of vector math, but it turned out to work out pretty well. And of course, those are just two examples, but there were a lot of similar calculations done for each type of actions. Like, for example, we could make indirect passes of the ball to our units. So there were a lot of domain-specific, game-specific math computation just done to generate those actions that the agent should use. And of course, we had to take into account the physics interactions that we have, but it turned out that it was pretty simple. We just could calculate simple circle collisions and level bound checks, so that we don't, because if you try to go out of bounds, the unit will fall, and it won't be able to move next turn. So it turned out that the whole physics is not really that complex, and we just could put all of that into the forward model. Okay, but still, even though we tried to limit the search space as much as possible, and of course simplify the game model as much as possible, still there were 11 to 20 possible actions per unit per turn. There were 2 players, 4 units per player. The movement order could be arbitrary. So, and by analyzing the game tree, we found that you have this level of complexity. So given that we could realistically perform maybe 20,000, maybe 30,000 of MCTS iterations, it was simply not enough to explore this kind of a huge space. So we applied a couple of tricks. First, we selected the movement order heuristically. So instead of, we just removed the select unit action entirely from the forward model, and we used a heuristic based on distances to the ball, to the opponents, to the goal, and so on. So it turned out that it worked pretty well, and it was just based on the human experience. So it was another part of game-specific, domain-specific knowledge that we have to encode into the forward model. This was an easy condition for early termination. So if you lose the ball, you just score 0, and that's all. So you didn't have to do further simulations. Of course, we had to do early termination after 1 round, because you can see that even 1 round, meaning my round and my opponent's round, has this degree of complexity. We had to do early termination after that, because going any deeper wouldn't be feasible. But still, even after limiting ourselves to 1 round, we found that we can achieve great performance by introducing rule-based opponent simulation. So instead of using the normal MCTS exploration for the opponent's turn, we could swap it out with simple rules that were also provided by human players. So as you can see, to make the whole approach feasible, to achieve like good enough performance and response time, we had to encode a lot of just human knowledge into that model. And of course, we wanted to give some designer control over the whole thing. So we implemented a custom evaluation function that was composed out of different components, like a bonus for moving forward, for breaking the defense line, and so on. But it turned out that, okay, this is good, all good for playing the attacking team, but defense is something completely different. And this is just an example of calculating the movement scores. So we calculated paths towards the goal, and we just gave the reward for moving along those paths. Okay, but yeah, we forgot about the defense, and it turns out that it's something completely different from playing the offensive side, because the criteria, the optimization criteria, are completely different. First, you have to stay as close to your goal as possible. You have to cover as much territory so that your opponents can get through, and you have like. Your main goal is to prevent the opponent of passing through the defense line. So the nature of the evaluation function is completely different. Like you have to think geometrically instead of in terms of like scores based on different parameters. Okay, so this is the thing that a human player playing in defense would do. So they try to cover as much of the movement fields of the opponent as possible, so that next turn, wherever the unit with the ball moves, they have them in range. So this is the main requirement for the AI playing in defense. But still, even human players make those kinds of mistakes. Like they can leave out a small portion of the movement field, and it may seem not significant, but really those kinds of micro movements make all the difference in the game. So what we did is we were looking for any kind of way of representing like basically it turns out polygons, but we wanted to reason about those movement fields and check their intersection and so on and so forth, and especially detect those kinds of places where the movement field the enemy's movement field wouldn't be covered by our own movement field. So it turns out that it's a solved problem. And there are existing libraries for polygon clipping. And we just went with a shipped one called Clipper. And we could like simplify the whole movement field that was continuous with a jagged polygon. And from the enemy team, from the attacking team, we could take only like the front of those movement fields, and it was created by just summing up the front parts of the movement fields, and then do the intersection with our own. And this way we could calculate the areas of the fields that are not covered, and we could detect those pesky little parts that cause so much trouble for the defending player. And it turns out that it worked pretty well, and it was even faster, like performance-wise, than playing the offense. So if you have like a geometric problem in your game and you really care about, like space coverage, or I don't know, if you want to cover most of the level with your line of sight and so on, you can simply use existing polygon clipping libraries, and they will just work. They are super performant. And this was in C#, so I guess that C++ libraries are even more performant. All right, so to sum it all up, I wanted to show you a little demo, but I have just 1 minute left. So maybe I'll show you just a part. So here you can see AI versus AI. So this is the reason why it's playing in editor, because the AI versus AI mode is only available there. And you can see that it still can take a little bit of time to calculate the movements. And probably, I'm not sure how clear the thing that's happening on the screen is, especially due to the resolution, which is super low for some reason. You can see that those units collaborate. They plan their moves, anticipating the moves of other units in the team, but also of the opponent team. And it really like it would be best if you just play the game, because the feel of it as you play against the bot is really human-like. We tried, and even we used the bot to onboard new testers to the team, so they could learn from the bot. And you can see a great example of collaboration here, where you evacuate basically the ball from the side of the field, and you pass it down to the next unit, and you can like plan long term to achieve the intended result. All right. Okay, so just to wrap it all up, the thing that went very well is that we achieved the quality that we intended. And we could, like, this is the biggest win. We could onboard new team members so they could learn the game from the bots. But unfortunately, like, the project got canceled. But the upside is that you can play it and you can see for yourself that this is real. That this is not some pie in the sky idea. It really works. You can use MCTS in tactical games, but you have to take into consideration all the work that you have to do to build the forward model, basically. So don't fool yourself that you'll just apply a magic algorithm to the game and it will work. All right. So I guess that this concludes the talk, and thank you. If you have any questions, just ask me on the Discord server or directly here. Right, thank you.